In this last video for week 6, we're going to talk about the homogeneity of proportions tests. And this is kind of what it sounds like. We are testing a claim about a single categorical variable, and we are comparing the distribution of that categorical variable between two populations. So this is a little bit different than our last two tests. Reminders that the goodness of fit test was looking at a single categorical variable between a population of values and a predicted distribution. The geneticist model of mice, for example, or the manager's assumption that the days that an employee is absent occur with equal frequency. For a test for independence, we're comparing two different categorical variables for a single population. For homogeneity of proportions, I'm looking at a single variable and I'm comparing the distribution between two populations. So this is the only type of test where we should have two different samples. So the labels along one side of our two-way table are going to be categories. The labels on the other side are going to be populations. This is sometimes easy to confuse with tests for independence because sometimes how we group our populations can look like a second categorical variable. The upside is that as far as our calculator is concerned, this test runs identical to a test for independence. So if you accidentally think you are performing a test for independence when it's actually homogeneity, the math doesn't care. The only time you're going to run into issues is when it comes time to interpret your answer. So one of the things you really need to look out for is wording in the question. Tests for independence are usually very clear in that they ask you to test if the two variables are independent or if there is a relationship. Here, it's going to be very clear that you are comparing two populations, and that is unique to tests for homogeneity. The upside is that this mostly looks familiar. The state step looks exactly like it did for a test for independence, including how we calculate those expected values and the fact that the calculator will do it for us. We know in the plan step, it's the same check for all chi-squareds. We're checking that our expected frequencies are 5 or greater. If we want to calculate our test statistic by hand because we enjoy those calculations, the formula for that is the same, observed minus expected squared divided by expected, add them up for every box in the table. And we're back down to a single categorical variable, and so k is typically number of categories minus 1, though if you forget and you do number of rows minus 1 times number of columns minus 1, you should get the same answer, because we're only comparing two populations, and 2 minus 1 is 1. That won't affect your answer. Quick reminders, because we are working with two-way tables, this is going to work exactly like it did for a test for independence. You're going to have to enter your data into a matrix either on the TI-84 or on GeoGebra. And the function call is exactly the same. On your TI-84, you're doing chi-squared test, and you're going to tell observed A, expected B, and run calculate. On GeoGebra, observed in matrix A, chi-squared test, the name of your observed matrix. So in terms of the calculator math, exactly the same as our last test. Let's go ahead and do two quick examples to see how this test runs and how it's a little bit different than our previous tests. So this first example says, do families and singles have the same distribution of cars? Use a level of significance of 0.05. Suppose that 100 randomly selected families and 200 randomly selected singles were asked what type of car they drove: sport, sedan, hatchback, truss, or van SUV. The results are shown on the right. Do families and singles have the same distribution of cars? Test at a level of significance of 0.05. The clue for me that I know I'm doing a test for homogeneity is I see one categorical variable, which is distribution of cars. I see two populations, families and singles. So two populations, single categorical variable. This is a test for homogeneity. Do those two distributions in the two different populations match for this categorical variable? The two-way table they gave me is the observed data. I know that my null and my alternative, the null is the distribution for families and singles matches. I swear I know how to spell. And then my alternative is the distribution for those two groups do not match. We are doing a chi-squared test for homogeneity. And I know that my check, I want to make sure that my expected are all greater than or equal to 5. And I'm going to check that after I do my calculator math. I know for the calculator math, I'm going to run chi-squared test on my calculator. It's going to ask me for the matrix where I put my observed. It's going to ask where I want to put my expected. Oops. And then it's going to spit out three things. It's going to give me my test statistic, my p-value, and it's going to confirm my degrees of freedom. And I'm going to check here. I count 1, 2, 3, 4, 5 categories. 5 minus 1, I expect a degrees of freedom of 4. So let's go ahead and set up our matrix. Second x to the minus 1. I want to edit matrix A. I have 2 rows and 5 columns. And then I go stat test, option C, chi-squared test, and I run to calculate. So it gives me a test statistic of 62.9, that's huge, and it gives me a p-value of 7.1 e to the negative 13. So that's 12 zeros followed by a 7. That's approximately 0. And it does give us that correct degrees of freedom of 4. Let's go ahead and check our expected matrix. So that's matrix B. And I can see that I think the smallest value is 11. So we've definitely cleared that bar of our expected values being 5 or bigger. I'm going to go ahead and draw my curve. So I'm way out here in the tail, 62.9, and I can see that my p-value is approximately 0. And when our p-value is low, we reject HO. So because our p-value of 0 is less than our significance level of 0.05, we reject the null hypothesis. Therefore, we do have sufficient evidence to support the claim that the distribution of car types for families and singles are different. They do not have the same distribution. Let's go ahead and try one more, make sure we've got it down. Second example says Ivy League schools receive many applications, but only some can be oops, sorry about that. Try that again. But only some can be accepted. At the schools listed and on the right, 2 types of applications are accepted, regular and early decision. We want to know if the number of regular applications accepted follows the same distribution as the number of early applications accepted. State the null and alternative hypotheses, the degrees of freedom, and the test statistic. Sketch the graph of the p-value and draw a conclusion about the test of homogeneity. So this one was really nice. They told us test for homogeneity. They didn't give us a level of significance, so we're going to assume alpha is 0.05. I know that the values in this table were observed between the regular applicants and the early applicants. We know that for a test for homogeneity, the distribution for regular apps and early apps match. And then the alternative is the distributions do not match. We are doing a chi-squared test for homogeneity. And we know the check is we want all expected values to be greater than or equal to 5, which we'll do after we run the test in our calculator. On the calculator, we call the chi-squared test function. It's going to ask, where is the observed? Where do we put the expected? And it's going to spit out our test statistic, our p-value, and our degrees of freedom. And we're going to go ahead and calculate those ahead of time. 1, 2, 3, 4, 5, 6. 6 minus 1 is 5, so I'm expecting a degrees of freedom of 5. Let's go ahead and put our data into the calculator. So second matrix, I want to edit matrix A. I have 2 rows and 6 columns. Whoops. And then I'm going to run chi-squared test. So stat test, chi-squared test, A, B, calculate. And we get even bigger values. We get a test statistic of about 430, a p-value that is a decimal point and 90 zeros, and then a 9. So that's definitely approximately 0. And we do get a degrees of freedom of 5. We're going to go back to our matrix menu. We're going to check B. And all of those values, if I come down here, I scroll all the way out, my smallest looks like it's in the hundreds. So I very clearly clear that bar of greater than or equal to 5. Much like our last example, I'm going to draw my picture, and then I'm going to state my conclusion. So chi-square curve, I'm way out here at 430, and my p-value is 0. And since our p-value is low, we reject HO. So because our p-value of 0 is less than our level of significance of 0.05, we reject the null hypothesis. We therefore have sufficient evidence to support the claim that the distribution of applications for the regular application and early applications do not match. All right, so those are the 3 tests that we perform for categorical variables. If you have any questions, feel free to send me an email or drop by office hours. There's also a short cheat sheet on how to tell the difference that I posted in Canvas on our resources page for week 6. I hope to see you during office hours this week. Otherwise, I'll see you in our week 7 videos.